Dark matter might be the strangest thing in the universe, and one scientist thinks he may have finally seen it in action. But here's where it gets controversial: is this really the first direct glimpse, or just another cosmic false alarm? For decades, researchers have been chasing dark matter, a mysterious, invisible form of matter that seems to dominate galaxies and shape the large-scale structure of the cosmos. Unlike ordinary matter, the stuff that makes up people, planets, stars, and everything you can see, dark matter does not give off, absorb, or reflect light, which is why telescopes can't capture it directly. Yet its presence is strongly suggested by its gravitational pull. Galaxies spin too fast and clusters of galaxies hold together more tightly than visible matter alone can explain, so something unseen must be adding extra mass. To bridge the gap between current physics and what astronomers actually observe, scientists propose that vast quantities of this missing matter must permeate the universe. They infer its existence not by looking at it, but by seeing how it tugs on stars, galaxies, and clusters. For almost a century, this has forced physicists to treat dark matter as a key ingredient in their models, even though they had never detected it in a direct, unambiguous way. And this is the part most people miss: almost everything we say about dark matter until now has been based on indirect evidence, not on catching it in the act. Now, a Japanese astrophysicist, Tomonori Totani from the University of Tokyo, says he may have detected the first direct signal that points to dark matter itself. Working with data from a region near the center of the Milky Way, he identified a diffuse glow of gamma rays forming a halo-like pattern in the sky. According to his analysis, this pattern could be consistent with dark matter particles surrounding our galaxy, interacting in ways that produce high-energy radiation. If true, it would be a historic breakthrough, the first time scientists move from merely inferring dark matter's presence to actually observing its possible fingerprints. Totani has described his reaction as one of intense excitement, comparing his odds of success at the start of the project to winning the lottery. His study, which appears in the Journal of Cosmology and Astroparticle Physics, uses observations from NASA's Fermi Gamma-ray Space Telescope, an instrument built to capture gamma rays, the most energetic form of electromagnetic radiation. In his work, Totani reports a gamma-ray signal with an overall brightness roughly 1,000,000 times fainter than the total light output of the Milky Way, yet spread out in a smooth, halo-like structure rather than concentrated at a single point. Dark matter itself has a long and curious history. The idea was first put forward in the 1930s by Swiss astronomer Fritz Zwicky, who noticed something odd about how galaxies moved in a massive cluster known as the Coma cluster. The galaxies were whirling around so quickly that, based on visible matter alone, they should have flown apart. Instead, the cluster remained bound together, implying that some additional, invisible mass was providing the necessary gravitational glue. That puzzle launched decades of research into a form of matter that appears to be everywhere, yet refuses to show itself directly. Over time, astronomers have concluded that dark matter must be truly unusual. It neither emits light like stars, nor reflects or absorbs it like dust and gas, making it effectively invisible across the electromagnetic spectrum. However, because it still has mass and occupies space, its gravitational influence can be measured in many contexts, from the rotation of galaxies to the bending of light from distant objects. Different theoretical models attempt to explain what dark matter is made of, but most agree that it likely consists of particles unlike the familiar protons, neutrons, and electrons in ordinary matter. One especially popular idea is that dark matter is composed of hypothetical particles known as WIMPs, short for weakly interacting massive particles. These particles would rarely interact with normal matter, which explains why they have been so hard to catch in experiments. In many versions of this theory, when two WIMPs collide, they can annihilate each other and release energy in the form of gamma rays. That's why astronomers scour the sky for unusual gamma-ray patterns. Such patterns could be the smoking gun of dark matter interactions. In Totani's case, the gamma rays he studied appear distributed in a roughly spherical, halo-like shape covering a wide swath of sky near the Milky Way's center. If the signal came from a single compact object, such as a black hole or an unusually bright star system, the gamma rays would look more concentrated. Instead, the diffuse, symmetric structure he reports lines up more naturally with what you might expect from a halo of dark matter particles surrounding the galaxy and occasionally annihilating. He also notes that the energy spectrum and shape of this emission do not match any known pattern from typical astrophysical sources like stars or cosmic rays. However, here's where the debate heats up. Several scientists not involved in the study are expressing serious caution, and some are openly skeptical. One major challenge is that gamma rays can be produced by many different high-energy phenomena in the universe, and astronomers do not yet have a complete catalog of all possible sources. Fast-spinning neutron stars, pulsars, black holes devouring ordinary matter and launching violent jets, and other exotic objects can all generate strong gamma-ray signals, sometimes in complex and poorly understood ways. Because of that, critics argue that it is extremely difficult to trace any particular gamma-ray glow back to dark matter with confidence. One physicist points out that researchers still lack a full understanding of the processes that create gamma rays throughout the cosmos, making it risky to jump to a dark matter explanation first. Another expert notes that the region of the sky Totani examined is, by its very nature, one of the hardest to model. The center of the Milky Way is crowded with stars, remnants, gas, and dust, and many overlapping sources can blend together to mimic a diffuse, halo-like signal. This complexity means that even when astronomers detect strange or unexpected gamma-ray emissions, it can be remarkably hard to draw firm conclusions. Subtle assumptions in how background emissions are modeled, or how known sources are subtracted from the data, can dramatically change the final interpretation. Some researchers therefore stress that any claim of seeing dark matter in such a messy environment must be treated with extreme caution. They also emphasize a long-standing principle in science: extraordinary claims demand extraordinarily strong and reproducible evidence. Still, not all reactions are dismissive. Some physicists describe Totani's work as interesting and worth keeping an eye on, even if they doubt that follow-up studies will fully confirm his current interpretation. They point out that the quest for dark matter has been ongoing for many decades, spanning underground detectors, particle accelerators, and space telescopes, and that any promising lead deserves scrutiny. Even if this particular signal turns out to have a more mundane explanation, the techniques and data analysis strategies developed could help guide future searches. If dark matter were finally detected in a clear, direct way, the impact would be enormous. Such a discovery would transform understanding of how the universe formed and evolved, since dark matter plays a central role in shaping galaxies, influencing how stars and planetary systems eventually emerge. It would also open a new window into physics beyond the current standard model, possibly revealing an entire hidden sector of particles and forces. In that sense, confirming dark matter's particle nature would not just solve a long-standing astronomical puzzle, it would fundamentally change how humanity understands its place in the cosmos. Totani himself acknowledges that more work is needed. He has expressed confidence in his analysis, but he also recognizes that the stakes are so high that the broader scientific community must carefully test and, ideally, independently reproduce his results. He expects other researchers to revisit the same data, apply different methods, and look for supporting or contradictory evidence. Only if multiple teams arrive at the same conclusion will the community start to accept the idea that this gamma-ray halo truly reveals dark matter. So where does that leave us? At a fascinating crossroads between excitement and skepticism. On one hand, there is the tantalizing possibility that scientists have finally found a direct sign of the invisible matter that makes up most of the universe's mass. On the other, there is the sober reminder that the universe is full of energetic, complicated processes that can masquerade as something new. Here's a question for you: do you think we are on the brink of a genuine dark matter breakthrough, or is this just another overhyped signal that will fade under closer inspection? And if you had to choose, would you rather scientists be bold and risk being wrong, or cautious and risk overlooking a revolutionary discovery? Share where you stand. Is this evidence convincing, or are you still unconvinced?